All right, so happy Halloween or Diwali or whatever you might celebrate today. This week has been this open lab for this input modeling report, so you can gather some data, not all of the data, for your final project, and generally use the input modeling report to propose the system that you're going to study and the data that you're going to work with, and so on and so forth. So that is due this weekend. So Sunday, the format is online. Um, Next 2 weeks, and there's also samples online next 2 weeks, Lab 9 and Lab 10. Lab 9 on the output analyzer, which we'll talk a little bit about as well as we get into validation more. And then Lab 10 on more advanced topics in arena like batching and so on. So, which might be helpful as you're building your models and making them a little more realistic. And then after that, there's no more labs scheduled. So that lab time is meant to provide you extra time to work on your projects and to meet with the TA to get help on those. So project, seen this, input modeling report, that's the big thing. Group submission. Once you submit it, I'll go through them and give feedback on what I think is this a good system? Is this a good choice of metrics and so on and so forth? So I will try to get that feedback back to you as soon as possible. It is definitely okay if you do not capture data for all of your inputs. I just need some evidence that you have access to the system and you are ready to go into the input modeling process, so that then I can feel confident that you can then go on your own into the process of drawing the diagrams and then eventually putting those models in. I want to see this because what I don't want to happen is, you get to the last week of the semester, you can overnight a diagram, but you can't overnight data collection. And if, you find out that, oh, you do need to go out and collect some data because this has to be kind of a real world model, then it's really hard to get that done kind of last minute. And so that's why I at least want to see that you do have access to the system, you can get some data so that you definitely will have some baseline connection to the real world system. The report should demonstrate you've chosen a feasible direction, and the desired format and everything again is online. I put some sample modeling reports from previous semesters online as well. Otherwise, ICAs, homework H, and then only one more homework left, and that homework can't be dropped because we use it to collect some ABET metrics, and that's it. So questions, pretty much no major updates since last time. All right. So, like I said, happy Halloween. So this is a Halloween themed lecture because it always seems to fall right here on this day or around this day. And that actually works really well because Halloween is a great time to talk about type 1 and type 2 error, as we will see in just a moment here. So remember, we're going to use the terminology that it's positive to detect a difference from the null. So even if you're doing a goodness of fit test where you're saying, are these data normally distributed or are these data exponentially distributed? If you detect that they're not, that might be a negative qualitative result for you, like, oh, I really wanted them to be exponentially distributed. But it's positive by our choice of language because you have managed to detect a difference from the null. So detecting differences, like, and I guess the reason why we view that as positive is, like I was saying, that we've said before that if you have very little data, it's impossible to detect a difference from a null. So it is a positive result in that, oh, I've gathered enough data that I actually can detect an effect, and that's why it's positive. So, significance level are probability of false positives. So that alpha, we're also going to call the FPR, the false positive rate. And that p-value, the probability of the deviation in our data being that large or larger if the hypothesis is true. So that p-value, generally any statistical test will give you a way to calculate the p-value, then it's up to you to choose the threshold. And so we will typically choose 0.05 in this class, but an interesting thing about it is that in other disciplines, in other application spaces, you swing that up and down. So if you're an engineering R&D team, you might be doing some preliminary research to try to find a new direction for your company to go in. And you definitely will follow up. You know, they will throw more money at this problem later, but they need to do some screening ahead of time just to find some possibilities. In that case, it is totally okay to ramp up your false positives because they don't want type 2 error. They don't want to miss anything. They want to detect, like, if we just use temperature in this particular way, then we can greatly reduce the cost of this process. Or if we start incorporating color in this display, then we will attract a lot more attention from people, and so on and so forth. So in that case, they are going to follow up. So when you are going to follow up with more work, you often will make the alpha higher because you know that you're going to be doing more tests to find out that, oh, that was just by chance we happened to find an effect in our in our pilot data, but then later on we followed up and found it wasn't there. But that's a lot better than missing something and then having a competitor find it. So in many engineering applications that we'll talk about, you're totally okay with an inflated alpha. So I'm going to talk about Bonferroni correction here today, but I will also talk about why a lot of engineers don't worry about Bonferroni correction, because in their application, and again, you guys don't know what that is yet, but we'll get to that, they're totally okay with an inflated alpha. There are other application spaces where you might want, and so another place where you're okay with inflated alpha you see is in bioinformatics. So in that case, you've got a huge amount of data that you've gathered from, from human specimens, medical data, whatever, and it's gigantic. And you're going to do these things like genome-wide association studies where you got all these data coming in and you're saying, we've got millions of people. Some of them have a particular disease, let's say Alzheimer's, others do not. And this kind of goes back to this idea for screening for piloting or whatever. So I'm going to look over these huge amount of expression data for this huge amount of people, and I'm effectively going to assign p-values to whether particular genes are tend to be correlated with the expression of that disease. And if those genes are tend to be expressed with that, then they are potentially targets for, say, pharmaceutical interventions later. That's a case where you're totally okay with having an alpha much higher because you definitely are going to follow up with more studies later. So if you're looking at huge amounts of data where it's meaning to be screening for later, you crank that alpha up. But if you're trying to make an inference about something that, you're the only one that's going to study it and your result really needs to stick and it better not be a spurious result, then you might crank the alpha down. So it really depends on your application area. Generally, we start at 0.05. There are historical reasons for that, but it is really a totally arbitrary threshold. Along, that's on alpha. On the flip side of that, beta, like I mentioned, for a lot of engineering applications, we actually care a lot about beta. We really want to make sure that we're okay with catching too many things because it ensures that other things don't fall through the cracks. So beta, the probability of not rejecting a false hypothesis. So if your hypothesis is false, failing to reject that it's false. The other way to view that is to flip it around, and this term statistical power, the probability of rejecting a false hypothesis. And so this is sort of whereas beta is a bad thing, statistical power is a good thing. So statistical power is our true positive rate. So if we fail to reject something, that's because it isn't actually there. And so if you really want high statistical power, then that might mean that you have to compromise on your type 1 error rate, but that might be something that's important for you. The other way that statistical power is used and what you'll use in your homework is figuring out how many samples that you should design your study to have. So for sim, samples are relatively cheap, although the bottom half of the class here, or the bottom third of the class, is going to be all about how do we build sims that use less computational time, less samples. That's going to be really important. But for really costly experiments out in the real world, then you really have to budget. You can say every time we run this replication, it costs $25,000. So what is the minimum number of replications for this particular experiment? In which case you got to do a power analysis ahead of time to say, all right, boss, what is the smallest variation you want me to detect? This is the second part of your homework. And the boss says, well, if it's less than one, whatever your unit of measurement is, if it's less than 1 watt, different than some power measurement that you're doing, then I don't care about it. That to me is equivalent, that those two systems, there's no difference there. But if it's greater than a watt, I really need to see that. So you can say, okay, so I'm going to set, I need to be able to detect 1 watt. And then I do some pilot studies and say, well, how variable is is the system that I'm studying? And based on the variability, every time I measure the system, how variable it is there, I use that standard deviation and that 1 watt threshold. And then I say, okay, boss, if you want to be able to detect 1 watt, you're going to need at least 20 samples. And so each one of those samples might cost a certain amount of money. So that's going to tell us how much we need to budget for this experiment. If we do more than 20 samples, then we're going to be more sensitive than we need to be. We'll be wasting money. But if we do less than 20 samples, then I can't guarantee you that we'll be able to see an effect that is of the size that you've provided. So that's what the power analysis does, is it helps figure out, given an experimental design, what is the statistical power, or given a desired power, what number of samples do we need? And that's what you'll practice on the second part of your homework. Now, all of that is stuff that, so that's the way we'll sort of talk there. And so, and there are different ways, different communities that kind of flip the meaning of these things. And you just have to be careful what community that you're talking about. So like, in this class, we typically say that this box up here, so the way you read these boxes is, so the null hypothesis here, we're saying that, if it's true, this is a universe where the null is true, then sometimes we reject it. We say that it's false, and that would be our type 1 error. So that's this box up here. In another universe where the null is false, there are errors we make, type 2 errors, where we fail to reject it, and that's this box down here. And then statistical power is this box, the complement of this one. And then this other box we don't have a good name for, well, at least not in this class, we don't have a good name for this box, and it's just the complement of this one. We don't really fit. So we focus mainly, we like these two boxes up here. We often talk about those, or these two boxes down here. But the terminology we'll often then use as shorthand is to say this type 1 error is a false positive. So for us, this is I call this kind of the alternative hypothesis centric, where the positive result is detecting an alternative, is saying it's not the null, it is something else. Finding that it is something else is a good, I guess, or a positive result. But there are other, a lot of times the public too will not think that way. And to them, this box would be a false negative, because they're kind of taking a null hypothesis perspective. It's like, oh, you were testing to see if it was normally distributed and you rejected the normal falsely. Well, that sounds, like it's the negative would be rejecting the normal, but it's like you falsely rejected the normal, so they're going to call it a false negative. So if somebody comes at you and they start talking about false negative rates and false positive rates, back up and make sure that you're talking about the same thing. That's one of the reasons we have this kind of cumbersome and ugly, terminology, or type 1 and type 2 error, because there's less ambiguity there. So, just make sure based on your context, if somebody's false positive is here or if it's down here. In this class, a false positive is type 1. Alpha is the false positive rate. But if you read, popular press or whatever, or just people just kind of just talking, then a lot of times what's positive, what negative is, flips. But just know in this class, positive is associated with alpha, and negative is associated with beta. So questions about that? Is that clear? Okay, great. So yeah, alpha and beta, and and Halloween or whatever. And so, the the idea of ghosts is actually kind of a nice motivational topic, because the idea of a ghostbuster is someone who has a high alpha. They are willing to believe you. They are willing to say that sound that you heard is maybe more likely than someone else would be willing to say, attributed to an interesting hypothesis like a ghost or something like that. So that's kind of something that sort of is going to be kind of a running comment here, is that this is what I mean by alpha being flexible, is that sometimes you have to be more tolerant of of alternative explanations, and sometimes you have to be less tolerant. And so the average person hears a bump in the night and assumes that it is the null, which is like a water heater kicking on. Well, the alternative hypothesis is that it's a ghost, right? And so you don't want to just say ghost unless, like most people, would not say ghost unless they had a preponderance of data. But there could be some individuals, perhaps especially when business is involved, that are willing to come out, and it doesn't have to be ghosts, it could be exterminators, whatever. You could say, I think I might have termites. Could you come out and spray? Very happy to spray, even though there's may actually be no evidence that you actually have termites there. But we're happy to we're happy to take your money. And so it's that's based on your agenda, your business agenda, and things like that. Then you might sometimes be more willing to accept less evidence for a given alternative hypothesis. So how do we often depict that? So this is the picture that you see usually in intro stats classes. And so, the idea here is that you have so this blue region I've labeled this section here as true negative, this red region true positive. The idea here is that you have results from a statistical test under different hypotheses. And so if I ran this test, so I gather data, I crunch the numbers, it generates a statistic. Under a certain hypothesis, the hypothesis here on the left, then there would be a certain distribution of statistical results. Under a different hypothesis, the hypothesis here on the right, there would be a different set of statistical results. So that distribution of that stat based on those data under different hypotheses. In other words, one hypothesis would generate data, a bunch of data that follows this distribution. The other hypothesis will generate a bunch of data that follows this distribution. And the problem is, if those two hypotheses don't have much of an effect size, so if they are very close together, so these distributions are on top of each other, then you could gather a bunch of samples and they will very often be in the overlap. And so what we're doing when we design statistical tests is setting this threshold, this vertical threshold here, where this correlates to our alpha, where we're saying that how far to the left does the statistic have to be in order for me to accept that, in order for me to conclude that it is a negative result, no difference from null? How extreme, how far to the right do the data have to be for me to assume that it is a positive result? So if I get data way over here, that's definitely to the right of this threshold. And, it seems very reasonable that over here, I would assume it comes from the alternative hypothesis. But if I got data over here, it's very reasonable to assume it came from the null. But if I get things in between here, that's where I get into these false positive and false negative. So I can have an extreme case from the alternative hypothesis that looks like the null, and I can have an extreme case from the null that looks like the alternative. And that's where we get the false negatives and false positives. And I throw this up here because if you have this in your mind and feel comfortable with this, then the trade-offs that I mentioned last time between false positive and false negative rate come right off of thinking about what happens as you sweep this bar to the left and the right. As you change alpha, so you change your false positive rate, you are just moving this back and forth. And so as you get the curves don't change, like the distributions don't change, just the cutoff point, the fence post doesn't. So as you move this fence post to the left to reduce the false negative rate, you necessarily inflate the false positive rate. As you move this to the right to deflate the false positive rate, you necessarily increase the false negative rate. So that's where the trade-off is. It's in this overlap between these two curves. So the more comfortable you become with this overlapping depiction here, then the easier it'll be to sort of think about how to make these choices. And that trade-off is captured in the so-called ROC curve that we introduced last time. And this is just a typical example here, where you plot the false positive rate on that one axis, the true positive rate, which is 1 minus the false negative rate. So this is alpha on the x-axis, alpha on the horizontal, and 1 minus beta on the vertical. And if your test that's generating data is just flipping a coin that is a biased coin, so it either always comes up tails 25% of the time, tails 50, tails 75, like maybe got that. But the idea is I'm switching, I'm going, always tails, 25% heads, 50% heads, 75% heads, always heads. If I just chose that, which has no relationship to my data, but when you ever ask me to make a decision, I flip a coin and I say, it's a negative result, or I say, it's a positive result, and I just do that based on the coin, then I'm going to get in this ROC curve this line here and that diagonal line. So that is our baseline. Any good statistical test will be pushed away from that line. So a good statistical test that is based on real data, like this one here, as you're changing this alpha, this horizontal axis, you're moving this vertical bar around, and it is then changing the balance between the false positive and the false negative rate, which is going to move you along this magenta curve here. And so every good statistical test will have some area between this relationship and this relationship. And some people measure that area and they call it the area underneath the curve. And so if you have multiple types of tests that you built for a particular data set, then you can compare them by their area underneath the curve. If you can manage to get this to be almost a step response, then that's like the perfect ideal test, where it makes like no errors, but that's usually never going to happen. So you're going to get something that's intermediate, that's like this. And so moving this around is equivalent to walking along this track here. All right, so any questions about this depiction? Just saying this because so far, alpha has not been something that's flexible, but in reality, it is very flexible. And so understanding this trade-off between alpha and beta, between alpha and statistical power, is important. Okay. All right, so example tests. And so you can, you will, if you get into data science, start to build your own tests, and there are different ways to do that. But what we do in this class primarily is design experiments that we then use. We design experiments for existing tests that are there, and the t-test is a very common one. So the t-test, is developed at Guinness Brewery by William Seeley Gossett. So this is kind of interesting story here. Gossett was an industrial engineer who worked for Guinness, the beer company, in the early 1900s. They would do, say, changes in their recipe for beer, and it would take a while for them to figure out, did their change have an effect on taste? Did people perceive the change? There's all of these different observables that you want to figure out. How can we determine if this change in our process made an observable change without us having to generate a lot of data, to try to do a lot of different tests? And because at that time, statistics in the 1900s was based on basically agricultural applications where you had huge fields. And so you could have one huge field where you did a process one way, another huge field where you did a process another way, and then each plant would be like a replicate of an experiment. So you got like 1,000 replicates here and 1,000 replicates here. And at that point, you had so much data, you just said, what's the average growth of these plants? What's the average growth of these plants? You just compare averages, point averages, and that was usually pretty safe. But Gossett said, well, what if we could figure out a way to come up with sort of a small sample statistical method where we could squeeze 10 samples for as much data as they're worth. And so Gossett went and worked with Ronald Fisher, one of these statisticians that had been working in the biology and the agricultural spheres. And he worked with him to build the t-test. And he came back to Guinness, and it was a great success at Guinness. And Gossett said, you know what, this has really helped our process here, but I really think this should be released to the world, because yeah, it might help our competitors, but there's a lot of other industries that we don't compete with that could benefit from the t-test. And so Guinness said, well, they had IP laws back then, and they had non-disclosures and all that sort of stuff. And they said, well, you can't publish under your name because that's just against our laws. But sort of, we do kind of agree with you that you should be able to publish this. So publish under a fake name. And that's where we got the so-called student's t-test, is that Gossett published under the name student. And so I kind of hate that it's called student's t-test, because when I was in your shoes, then the first time I learned about the t-test, I thought it was just sort of this fake test that was created for academic exercises, so it was like a sort of a baby statistical test that nobody actually uses. So it's like I was the student and it was the test that was like for me to warm up to the real test. But no, that was just a fake name that Gossett published under in order to get it out to the world. And then later on, people realized that it was Gossett. And so, but Gossett was also very shy. And he said that, so there was I'm sorry, I said he worked with Fisher, he worked with Pearson. But then later, when people said, "Oh, this t-test is really helpful," you should. This is an amazing accomplishment, and he would always say, "No, no, Fisher would have figured it out eventually anyway." Like, so he was always very humble and sort of assumed that anything he'd done would have been figured out. So I don't think he minded that he had to publish under this other name. But it's just kind of, I think, interesting story here. And then people like Fisher end up saying, taking the t-test and generalizing it into the ANOVA, which is basically the t-test with multiple groups. So t-test is like you're comparing two groups together. The ANOVA is you're comparing like 5 groups together, but both of them are saying, are the means different across these groups? And then later on, it got generalized. And so the t-test requires your data to be normally distributed. There's a so-called U-test that when your data aren't normally distributed, so when they fail the Shapiro-Wilk test for normality, then there is a non-parametric, and we'll learn about what that means later, but there's a non-parametric version of the t-test that does not have as much power as the t-test, but can be used when your data aren't normally distributed, and that's the U-test, T-U. So yeah, a lot of generalizations. So very powerful test. But how does it work, and what is it? So the one sample t-test tests to see whether a population mean of a bunch of data is equal to a specified hypothetical value. So your null hypothesis is the mean of the population is equal to a given mean. So I collected a bunch of data and I need to test. I expect that if my beer is good, then this particular quantity, it's the average amount of crap floating in the beer or whatever after the process, is equal to this given amount. So I'd like to test for that. That's that I want to detect a difference from that if there is one. And it's a one sample t-test because this is when I don't know if it's confusing to you guys. When I was in your shoes, this term was very confusing to me. Then what do you mean one sample? I just took 30 samples and I plugged them into the data. Where does this one sample come into? And the idea here is that the math of the t-test is based on the average. So it's actually sampling an average. And so it's like you took 30 data points and generated one average. Well, you could have taken 30 more data points and generated another average, and then 30 more data points generated another average. So this is a sample from the distribution of averages. So it's not referring to the data you gathered, it was referring to the estimate of the mean. That is the sample. That's where the one sample comes from. So you just basically take the estimate of the mean minus your hypothetical mean and divide it by something that looks standard deviation E. So the standard deviation of the data divided by square root of n. And there's a reason why this looks a little bit like a z-score, which we'll get to here. So that's the t-test. What do we need to make the t-test work? Fortunately, when you're working with SIM, these assumptions are very often going to be met automatically if you're comparing data across replications. Within a replication, this is not always the case, and we'll talk about that when we get to batching. But across replications, usually you get this for free. In real world experiments that you'll do as an industrial engineer, this is not always the case. And that's why we have things like Shapiro-Wilk and so on. So in order for the t-test assumptions to work and this test to be meaningful, your data have to be independent. So every sample has to be independent of the previous samples and drawn from a normal distribution. So under those cases, if that's the case, then this statistic will have a so-called student's t-distribution within -1 degrees of freedom. And what that basically gives you a distribution that you can plug in to a picture that looks like this. And that's what the tables in the back of the book are doing, is they effectively, this blue bar, this blue thing here, that is the student's t-distribution, and the alpha that you choose sets the threshold value of where you cut off from that student's t-distribution. So let's see what that looks like. So where do these assumptions come from? Well, under the null, we are going to say, or just assume every point's independent of every other. We're going to assume they're normally distributed with the same mean and the same variance. So under that case, let's consider this random variable. This is that one sample that I was talking about. And so, it's just the sum of all your data divided by however many points you have. That's just our formula for sample mean, which we can do some rearrangement of. And under the null, the expected value of this thing, y bar, is equal to the expected value of our sample data points. Okay, so if we assume our data points are distributed with mu as the average, then the estimate of this thing also will have that as the average. Good. So that means that if I subtract off the hypothetical under the null, then this quantity, the expected value of this thing minus the hypothetical, will be equal to 0. Okay, great. So that means that this is a so-called unbiased estimator of the mean. So the real mean is mu. This estimator is also mu. It doesn't have any shift to it, and so on. Great. So now the variance. So I want to know, what is the variance of this thing? Well, the variance of each individual sample, well, it's actually more, I care about the variance of the sample divided by n. So the variance of each one of these little bits is, if you do go back to probability theory, the variance of a random variable divided by a constant, this is a deterministic value, a scalar, is going to be equal to the variance of that random variable divided by the square of that sample. So I'm dividing by n, but I'm effectively then dividing the variance by n squared. So the variance of each one of these little guys here, divided by n, is going to be equal to the variance of the numerator divided by n squared. And so if I want to know what's the variance of the numerator of the t-test, the thing up there, that's going to be equal to the variance of the data that I was collecting divided by n. So I'm just basically taking each one of these and adding them together n times, because these are independent, the variance of the sum is the sum of the variances. So this is sigma squared over n squared, sigma squared over n squared, sigma squared over n squared. I have n copies. The sigma squared over n squared times n just gives me sigma squared over n. So finally, I take the square root of that whole thing. This gives me the standard deviation of this random variable here. And that gives me the standard deviation of my original sample data divided by square root of n. This is the formula of the so-called standard error of the mean. So what this is saying is, again, if I took 30 points, generated a mean, another 30 points generated a new mean, another 30 points generated a new mean, I could take all those means and I could put a histogram up of them. This will be the standard deviation of that histogram. So this is not the standard error or the standard deviation of your data. That's why it's divided by square root of n. It is the standard error of the estimator of your mean. That's a critically important thing, is that to keep in mind is that these y bar, that is itself a random variable. You can sample it multiple times and you'll get different estimates of the mean. And this is the standard deviation of that distribution. All right, so any questions about that? So we know we've got we're sort of figuring out the numerator and the denominator of this t statistic before we put it back all together. All right, so we know under the null that the mean of the numerator of the t statistic is 0. And we know that the denominator of the t statistic is this standard error of the mean of this thing up here. So by the central limit theorem, as the number of terms in this sum goes to infinity, then the numerator of that t statistic goes to a normal distribution whose mean is 0, because that's the mean there, and whose standard deviation is this standard deviation that we calculated here. So just under the central limit theorem, basically this sum here is not normally distributed for small n, but as n gets large. So this sum here, if you only add up a couple of terms and then you take a histogram of that estimate with only a couple of terms, that's not going to look like a perfect normal distribution. It'll be skewed, might be a little fatter on one side or whatever. But as you add up more and more, then this sum, this estimate here, will start to look normally distributed. And it will be normally distributed. If you subtract off the hypothetical mean, it'll be normally distributed with a mean of 0 and this standard deviation. So if we just divide it by this standard deviation, then that, and this is what we end up getting here, this becomes a z-score. So basically this thing, if we have a lot of data, will be normally distributed with a mean of 0 and a standard deviation of 1. So with a lot of data, that's the key point here, then this is just, you could use a z-test. You could just say, I'm going to calculate this, that will give me a z-score. And if that z-score is sufficiently large, if the absolute value of that z-score is sufficiently large, then I'm far away from my null hypothesis. I'm far away from the mean value that I assumed. But if it's really close to 0, then that is good evidence that my data actually had this mean. But that only works if you have lots and lots and lots of data, because it requires us to for this thing to be a standard normal. It requires this statistic to converge to a normally distributed curve. So what students did, what Gossett did, is he answered the question of what does this statistic look like for small n? And that's the so-called student's t distribution. So I put in blue the standard normal. And if I only have 2 data points, so this is so-called 1 degree of freedom, and it's 1 degree of freedom because I had to calculate the mean from those 2 data points, and that mean became a parameter. So I only have 1 degree of freedom left over. So that's why in the t-test, if you've sampled 40 data points, you're only going to have 39 degrees of freedom, because you had to sacrifice one of them to estimate the mean, to correct for the mean. We've got the blue one, that's our standard normal. This is the distribution of that thing. So this is the distribution of this statistic if I only use 2 data points. When each one of those data points is normally distributed, but I've only got 2 of them to put into the sum, this is the distribution of that thing I'm going to get. It's got really fat tails, and so it's shorter in the middle. It is not normally distributed. It's symmetric, but it's definitely not normally distributed. As I add more data, so now I'm calculating it based on 3 samples. So it has a degree of freedom of 2. It gets closer to the standard normal. I can keep doing that over and over again. So now I've got 11 samples, so 10 degrees of freedom, and I'm pretty close to the normal. By the time I get to 31 samples, so 30 degrees of freedom, then pretty much a t-score turns into a z-score. And so that's the magic of the student's t-test. It just fills in the donut hole. So if you have more than 30 samples, you don't need a t-test anymore. You pretty much can just use, if you can make these assumptions about independence and normality, you can just calculate a z-score and just use the z-tables. Like, you don't actually, I mean, you should use the t-tables because why not? But you may as well use, at that point, the t-test tables and the z-score tables are going to look identical. But under 30 data points, like Gossett, he's the industrial engineer, he is in the brewery, he doesn't want to have to run experiments that are this large. Then this allows him to say, oh, well, if I only gather 6 data points, this is the distribution I'm going to get. Now I can run statistics with this distribution instead of the standard normal. That's the innovation that Gossett had. So this is what we refer to as a pivotal quality. Its shape only depends on the degrees of freedom, and that allows us to set these thresholds so that we can say that if this statistic is greater than this threshold, we reject. If it's less than this threshold, we fail to reject. So, that's kind of what we're saying here. So, so this is just me saying a very rare is evidence of an unlikely, and so on. So the distance between, so this is kind of an interesting thing. In T space, you can then actually calculate, like, it's rescaling your data. So you can say my null hypothesis is centered at 0, but an alternative hypothesis that is also normally distributed, it has this effect size here. So if this is my null hypothesis and this is an alternative hypothesis, in the real world, this is like that effect size kind of I was talking about, like they said, well, I want to be able to detect 1 watt difference in power output. So, like, has the weather affected my generator? Well, I can measure the power output and it's going to be variable, but based on the samples you're getting, I want to detect a 1 watt difference or greater. I don't care about anything less than a watt. Well, that 1 watt is sort of, the null hypothesis is that it's normally a 300 watt generator. And, I'm trying to detect whether it is a 299 watt or a 301 watt generator. So I've got these alternative hypotheses. So the value up here, the difference between those is just a 1 watt difference. So what this is saying here is that the space between your hypotheses in the real world gets scaled into the space between T statistics by the standard error of the mean. So if you can make the standard error of the mean really, really small, then you are going to separate your hypotheses in T space. Because if you make the denominator of this thing small, you're going to make the distance in T space large. So that's why we gather more data. We gather more data because in our pivotal quantity space, it causes, in that picture here, it causes the blue curve and the red curve to separate. If you get less data, it causes them to come back together. That's how these statistics work. All right, so any questions about that? That's where the t-test comes from. I'm not showing how he figured out that they have fat tails and all of that. That's kind of, but I just want to see that that's the reason why we have the t-test sometimes, the z-test other times. The t-test is a donut hole fix for when you can't use the z-test. So when you have small amounts of data. Okay. All right, so back to the theme. So this is a grad student in, I think, biometry, so biological statistics at another university. I thought it was kind of a cute shirt here. So he's wearing this T-shirt that has a funny looking distribution, and underneath it, it says student. So, then the challenge would be, the midterm or final exam question would be to explain the joke, and so can anybody see the punchline here? So it's a student's T. So it's a student's T-shirt. So that's a student T distribution on a T-shirt. So, student's T-shirt, so on and so forth. So so he added to it by carrying around a bottle of Guinness and a box of tea for the night. So there you go. Now you're in on the joke. And the weekend is still up, so this would be very easy to make. So I just encourage you, white t-shirt, maybe some black electrical tape. This is yours. So, yeah, student's T shirt. I would add not a normal student. That would be another way to do it. This is not a normal distribution. The tails are too fat. So it's kind of a weird student. So that's something else you can add to it and so on. So anyways, t-test, students t. What if neurality doesn't hold? So this is starting to get a little outside of the things that I'm going to make you do in this class, but I want you to know that despite how powerful in many different forms of the word the t-test is, there are definitely data that you will get where you're going to want to test your data relative to a mean, where you're not going to be able to use a t-test because that data will not be normal. And so that's why we have these so-called non-parametric tests. So a t-test is a parametric test, which means you assume a distribution and your inference is just about the parameters of that distribution. A t-test is about, it's saying, I'm assuming the data are normal. All I need to know is the mean of that normal distribution. Is this mean within this other mean? If you can't assume they're normal, then you have so-called non-parametric tests. They have less power, so they're less sensitive. You need more data to detect a difference, but they work on a wider range of data. And I already mentioned some of them, like the Mann-Whitney U test, Wilcoxon signed rank test. This is the non-parametric version of the paired t-test. And the Kruskal-Wallis test, that's the non-parametric version of the ANOVA. So when you start into more sophisticated stats, typically you start with, at least if you're doing engineering, biometry, and so on, things are a little different with econometrics and such, but you start with things like the t-test, you build up to the paired t-test, you build up to the ANOVA, and then you build up to linear regressions and so on. And then after you get all of that in your head, then somebody says, okay, now none of your data are normally distributed. What are you going to do? And then you add to the little decision tree in your head, you just mirror this, and then you add these things, and you say, okay, the t-test, my analogous test is the u-test. The paired t-test, Wilcoxon signed rank. The ANOVA, Kruskal-Wallis. Or even if you don't remember them, as long as you remember that if it's not normally distributed, I need a non-parametric version. If you Google non-parametric t-test, the u-test will come up as the first thing. So just knowing to ask the question is important. So that's a little outside of the scope of the class, but I do want you to know that if your data aren't normally distributed, you should know this word, non-parametric. So you know the next thing to do is to find somebody to ask, what is a non-parametric ANOVA I can use? And then they can say, oh, look up the Kruskal-Wallis. And then you apply the data in the exact same way. You just had to know what the name was. And there it is. And then you'll find that in any good statistical program. And so how do you know if you have to use a parametric or non-parametric? That's why I introduced the Shapiro-Wilk, which is a very high-powered test for normality. So oftentimes, unfortunately, hypothesis testing involves a sequence of statistical tests to first see if you met all the assumptions of the tests and then do the tests you actually care about. All right. Before we do an example, which will be relevant to your homework, are there any questions about that? Okay, so relating to what we were doing last time before we stopped, so let's say I want to compare real and simulated system data. So in this case, I've got that bank or whatever that I've been running cars through, and I'm seeing how long they're waiting at these lines, and I've got a certain number of tellers and everything inside. And then I've got a simulated bank where I've got simulated cars going through the bank, and they've got simulated tellers and simulated wait times and so on. And I want to compare the real data to the simulated data. Now, in one of the examples we're going to do last time that isn't on your homework, but that is in the book, that I'm skipping over for time just to catch back up, you could just take an average of the real data and then use a t-test to test whether that average from the real world is, use it as the null for the data that come out of your sim. So you have a bunch of wait times that come out of your sim. You use just a one sample t-test with the average from the real data, compare those together. And if there's a difference, then that means that your sim, if it's set up to mimic the real world and you now notice this difference, you need to calibrate your sim. You need to make changes in your sim in order to bring it back together. This is a slightly different approach to doing the same sort of test and calibration, where I'm not going to calculate the mean of the real world data. I'm going to use the real world data itself. So I am going to feed, rather than random numbers into my sim, I'm going to actually take the real inputs, like the real inter-arrival times from the real world, and I'm going to pipe them into my sim. So I've got effectively the same customers in the real world. Now we're going through my virtual world. So there's no randomness. It's the same data. The world is my random number generator in this case. So for each real customer going through the real system, they're going to get a real performance metric. How long did they wait? But then that real customer going through my virtual system is going to get a virtual wait time. So now for every customer, I'm going to have a real wait time and a virtual wait time, kind of like what we did in the muffin making simulation, where we had one schedule of muffins, went through one batching process or another batching process, and then we got two performance metrics to compare. So we're going to then, you got real data and simulated data for each customer or each arrival. Because there's a lack of independence, I cannot compare the real performance data against the simulated performance data as a two-sample test. The lack of independence there, because one customer generated these 2 points. These 2 points are coupled together. They're paired. It's a blocked design. So I have to do something else. So instead, I'm going to measure the difference between the two. So this customer in the virtual system waited 2 minutes, and the real system waited 2.5 minutes. So for this customer, they generated a 30-second difference. That's what I'm going to do here. And then I can use a one sample t-test to say, is this difference significantly more or less than 0? Because if my two systems are very similar together, then I'll get differences, but those differences will be very tightly packed around 0 because the data will be coming from the same distributions. But if my simulated system is generating wait times that are from a different distribution than my real system, then I should see a signal. I should be able to see that there is a difference between these two systems. So I'm going to evaluate whether the average difference between the real wait times and the simulated wait times are equal to 0, seeing if I can reject that null. And I can then easily do a power analysis to see how many samples I need to do this evaluation to find the significant, to find whatever difference I think is actually realistically important. So let's see how we do that. Here's the data table. So this is going to be very similar to what you're doing on that homework. The second problem of the homework is you've got a column of output data from the real system, a column of output data from the simulated system. This is input set 1. So you can think of this as real data from Monday, real data from Tuesday, real data from Wednesday, or so on and so forth. So I pipe the same real data into the real system and into the virtual system. I get a real performance metric and a virtual performance metric for that day. And then in this column, this is my difference between real and virtual for that day's data. So I get a column of differences. This is the column that I'm wondering, is this distributed around 0? If it's distributed around 0, I'm okay with that. If it's distributed around 5, then that means that on average, there's a 5-unit difference between my simulated system and my real system. I need to calibrate my simulated system and fix that. So in order for me to calculate my t-statistics, I then need to calculate the average of this column and then calculate these squared deviations from mean. That will go into my variance calculations, or basically the standard error, the mean calculations that I use in the t-statistic. So I'm given this, I calculate this and this. And then again, normally I would use a 2-sample t-test to compare these two columns, but I can't for those reasons. So I'm going to use a 1-sample t-test to compare this column to 0. So what does that look like? Well, there's my null hypothesis is that this difference is equal to 0. Alternative is not. I can calculate a t-statistic here where I'm going to take the mean of this column minus 0 here. That is my null. That is my null hypothesis that there is no difference between these two, so that this column is distributed around 0. The mean of this column is 0. That is my null. So my t-statistic just reduces to the mean of this column right there, divided by the standard error of the mean. And that I get by calculating the standard deviation of this column divided by the square root of k, where k is my number of rows. So notice here, it's not k minus 1. It actually is k. So that gets confusing. Sometimes you use the k-1 to look up the critical values because that has to do with degrees of freedom. This does not have to do with degrees of freedom, so it is actually the value k. So this question 2 asks you, okay, given that you've done this, then how do you use a power analysis to figure out how many rows do you need in this table? So let's say every simulation takes 10 minutes to run. I actually have a simulation optimization problem I work on now for designing wetland configurations across the state of Texas. And every time I run a simulation of a new wetland configuration, it takes 10 minutes. But there are 2 to the 1,000 different combinations of wetlands that we are optimizing over. So that's like more atoms than in the universe. So I can't just do them all, at 10 minutes of simulation. So, you want to reduce your number of simulations. So, so how do we do that? So what we're going to do is we calculate this so-called effect size that we want to be able to detect. So we need to ask someone, a stakeholder, what is a meaningful difference between the simulated system and the real system? I know that if I gather enough data, I will eventually detect a difference between the simulated system and the real system. They aren't the same system, but how close do they have to be? And they might come away from that and say, well, as long as it's within, as long as this performance metric, like wait time, is within a minute, I'm willing to say that your sim is close enough to the real world that I don't need further calibration. Great. So, or 2 minutes. So maybe it'll make it more exciting. 2 minutes. So then I would set 2 to my difference here, but I have to scale it by the standard deviation. And that gives me sort of the number of standard deviations away from my null hypothesis that I'm willing to tolerate. And so that's what an effect size is it's a number of standard deviations away from the null that you're willing to tolerate as being okay to not detect. So as long as if it's more than this away, you better reject the null. But if it's within this amount of standard deviations, that's fine. That's what we mean by this effect size. So this is subjective. You have to I will give you in the homework this value. I'll say your boss said this value up here is 2.5. You're going to have to know to normalize it by the standard deviation and so on. But this is not, you can't infer this from anything. That just comes from somebody saying, this is the value. It's subjective. So there are questions about this. So somebody see what I mean by effect size. We have to calculate this before we can do the power analysis. Okay, so somebody gives us the big D here. We then calculate this effect size. They also have to give us the desired false positive rate. So we're going to do 5% as normal. And we have to know desired power. So the typical power that we choose in most of these studies is 80%. So 5% false positive rate, 20% false negative rate. That's usually what we tolerate. But these could be different. But let's just say, and I think this is what is in the homework, that as well. So, so with that, I have to turn to the so-called operating characteristic curves, which are in the back of the book. But nowadays, you use tools like in MATLAB or in R. There are tools that automatically can calculate this stuff for you, so you don't have to look it up in tables. But it's good, at least the first couple times you do it, to know that these tables exist and use them. So in the back of the book, they have a table for an alpha of 0.05. They have a table for an alpha of 0.01. We focus on the 0.05 table. So you zoom in on this, and remember that statistical power is 1 minus beta. And this operating characteristic curve in the back of the book is got beta on this axis here, not statistical power. So it's not an ROC curve like we had. So it's got beta here. So just remember that if I want an 80% statistical power, then I'm going to be looking at this 20% line here. So we've got effect size on the x-axis and false negative rate, or 1 minus statistical power on the y-axis. So in this particular case, if they said we wanted a 20%, then we know we're gonna be sitting on this line. And then we say, what is the effect size they wanted us to detect? How many standard deviations away from the null is okay? And if it's 1 standard deviation away from the null, then that means I need at least 10 samples. If it's 2 standard deviations away from the null, well, I know that if I did 4 samples, that's not going to quite be enough. If I did 5 samples, that's even better. So I probably have to go to 5 samples. Generally, as a hint, when I design these problems in the homeworks, I try to make it so that these curves intersect the line. So like in this case, like I probably would say this is a 1. I'd say this is probably 1.25. This is 1.5. So if I asked you for like a 1.25 effect size, then you don't have to fret and say, oh, I don't know, it's quite there, whatever. It's like, if I ask you for 1.25 and that is like suspiciously close to that intersection point, then I'm asking you for this line right here where it's okay to say 7 samples are enough. You don't have to sort of overthink it and say, well, I'm not quite sure where it landed, so I'm going to go to 8 samples to be conservative or whatever. So just as a tip for as you're doing this homework. But that's basically what you do, is that you use that table and to get your standard deviation. You use the minimum detectable difference from mean that your stakeholder has given you. You normalize it by that standard deviation to get the effect size. And then you then go back and say, what false positive or what false negative rate, what statistical power does my stakeholder is okay with? And then you find that and you find out where they intersect. And then you look at the curve that they intersect nearby, and that tells you how many samples you need. So that's how we do a power analysis for a t-test, for a 1 sample t-test. Any questions about that? That is basically the second part of your homework. Yeah. Homework H. Yeah. Okay. All right. So last things here is that the other big test that we use in the class is chi-squared. So there's this weird 5 threshold in chi-squared, and I just wanted to show you where that comes from. So remember the chi-squared, this is the statistic that you calculate, observed minus expected in your bins squared divided by expected. I think when I first encountered the chi-squared, when I was in your shoes, it looked weird. It looked like the units were wrong. The fact that the numerator was squared and the denominator wasn't. Like, why don't they divide by e squared, or why don't they, use an absolute value or something? Well, it's not a heuristic. It turns out there's real reasons they do this. And so if we look at this binary case here, so just for 2 bins here, then the chi-squared becomes this thing. And so this special case here, just remember that for 2 bins, there's only 1 degree of freedom. So if I know the observed counts in 1 bin, then I automatically know the observed counts in the other bin because I know how much data there are totally. So that will become important here. So the idea here behind the chi-squared is every bin can be viewed individually as its own tiny little binomial test. So you're counting things. Well, the other distributions we talk about in counts are binomials. And so remember, in a binomial test, it's given there's a certain probability of landing in this bin or in another bin. Given that I flip a coin 100 times and there's a certain probability of it coming up heads, landing in this bin, or coming up tails, landing in some other bin, then for 100 of those, what's the distribution of counts that I get in this bin? That is effectively what the chi-squared is doing for every one of its bins. But it's a pain in the butt to use binomial tests for each one of those bins. So it looks for a way to approximate the binomial test by a normal distribution. And that is where the 5 is going to come from. So the idea here is that, so again, there's our binomial test. If in a binomial test, you let the number of coin flips go to infinity, then the binomial test is well approximated by a normal distribution with this mean and this variance. That's just by the central limit theorem, which comes up over and over again. And so if I have a large enough number of expected counts, so that's this n times p, that's the expected counts in the bin, then the binomial distribution that describes the distribution of counts in the bin will be symmetric and bell-shaped, and it will basically look like a normal. and it will be far enough away so that it won't have a lot of counts that will show up in the negatives. So that's what we're doing by forcing the number of counts in the bins to be more than 5. So basically, if you think about it, a not a chi-squared, just a chi, like the square root of a chi-squared, is this statistic here, which is the observed number of counts in a bin minus the expected number of counts in the bin divided by the square root or divided by the standard deviation of the counts in the bin. That's a z-score for this approximation of the binomial distribution. So if I have enough counts, expected counts in the bin, I can replace a binomial distribution with a normal. Once I have a normal, I can characterize the normal by a z-score. That's where I got this thing here. So I just plug in, and this here starts to look a little bit like the chi-squared. It doesn't quite look that way because the denominator is wrong, but it starts to look that way. So this is a standardized score of the deviation from expectation for a single bin. So the idea here is that I can take that and then I do this partial fraction expansion. So some of you have probably done this in some of your other courses. If you do take any systems theory courses, you do this a lot. But basically, whenever you get something ugly like this that has a product in the denominator, you can turn it into this. There's a systematic way to do that. And it turns out that this squared thing allows you to do, like, I can't do a partial fraction expansion of this because the denominator is under a square root. But if I square this thing, the denominator is a simple product, and you can do this partial fraction expansion, which turns this one squared z-score into a sum of two things. That's where the -1 is going to come from in the chi-squared. There is only one degree of freedom here. It's the number of counts in the bin, because all the other counts are out of the bin. But when you do this partial fraction expansion, you get this beautiful structure where these two parts have the same way. This is the expected number of counts in the bin. This is the expected number of counts out of the bin. I'm sorry, this is the number of counts in the bin, the number of counts out of the bin. This is the expected in the bin. This is the expected out of the bin. And notice the numerator's got the square, the denominator's doesn't. That is a chi-squared statistic with 1 degree of freedom, with 2 bins. And so you can just generalize that, so that's what I'm saying there, to multiple bins, and that's where the chi-squared statistic comes from. So I think I've got, a bunch of sort of examples here of, well, maybe that's next time where I'll show you examples of this converging. But I just want to get, what I'm trying to share here is that 5, that whole thing is all about this continuity here, is that if you don't have an expected count of 5 or more, you have to use a binomial test. And all of this approximation stuff, the partial fraction expansion, whatever, is invalid. It just does not apply at all. So that's where the 5 comes from. It's not some weird made up term. It is exactly due to that. All right. So, and then there's a bunch of sort of bonus things there, but that's, and then I just sort of got some musings for if we had time, but which we'll talk about Bonferroni later anyway. And that's pretty much all I've got for you. So I don't want to keep you any, now that we're back on schedule. So let's do a clicker question. And so the question I guess we'll do here is, what name did William Seeley Gossett have to publish his work under? So what is the name that was used to publish the key contribution of the Guinness industrial engineer, William Seeley Gossett? He just had to publish under a name. Guinness couldn't let him publish under his name. So what name did he use? And otherwise, hope you have a nice weekend. Don't forget to make your shirts. Black electrical tape works well. Mhm. Have a good day. Have a good day.